Hello guys, welcome back to the channel Mathemagix JEE. This is part of the CBQ series or the concept building question series where we are going to solve specific problems to develop our thinking capability for JEE Advanced. This is the question number 3 of that series. As always, I would advise you to give an honest attempt to this question before seeing the discussion. So, what does this question say? It says if f defined from set of real numbers to set of real numbers be a differentiable function satisfying this functional relation for all n belongs to natural numbers, then which of the options are correct? This is a multiple choice question, so one or more than one options can be correct. So if we look into the options, here it says that fx is a bijective function in R. So what is bijective function? A bijective function is both one and onto function. So the first thing that strikes our mind is that if we want to check whether this function fx is bijective or not, we have to check the monotonicity of the function. So we are given this functional relation here. And as it is given that f is a differentiable function, we can differentiate both sides with respect to the variable x. So we differentiate both sides with respect to x. We get this will be 2n plus 1 f of x whole to the power 2n times f dash of x is equal to 1 minus this will be f dash of x. That means f dash x will become 1 over 1 plus 2n plus 1 times fx whole to the power 2n. This is the expression we got for f dash x. Now we can see clearly that f dash x is clearly greater than 0 for all x belongs to real number. That means fx is a function which is strictly increasing. So the function is like this. This is y equal to f of x. Now how to check whether fx is onto or not? So we assume that f inverse x exists. Okay. This will be our approach. We assume that f inverse x exists, so f must be a bijective function. By this assumption, if we want to calculate f inverse x, we will substitute x equal to f inverse y in this expression. Because y is fx, so x is f inverse y. That means we get f of x will be y, so y to the power 2n plus 1 plus this will be y equal to f inverse of y. Now here we can simply replace y with x. That means f inverse x comes out to be x plus x to the power 2n plus 1. Now we can check directly the behavior of f inverse x. F inverse x is 1 1 of course, because fx is 1 1. But if we want to check the behavior of f inverse x, we would tend x towards minus infinity and towards plus infinity. When x tends to minus infinity, f inverse x tends to minus infinity, because this is some odd power of x and this is plus x. And similarly, if I tend x to positive infinity, this function will go towards infinity. This f inverse x is onto. So we calculated that f inverse x is onto. That means definitely fx must be onto, and our assumption is correct that f inverse x exists because fx is both 1 1 and onto, so fx is a bijective function. That means f inverse x exists and our assumption is correct, and f inverse x is also onto. How can we say that? If we draw the line here, y equal to x, like this, y equal to f inverse x will be simply the mirror image of the function y equal to fx about the line y equal to x. So the f inverse x will look like this. And we can say that if y equal to f inverse x goes towards infinity and this side goes towards negative infinity, then fx should approach negative infinity and positive infinity also. That means if fx is onto, f inverse x is also onto. So we can say that the first statement, fx is a bijective function in R, is absolutely correct. Now let us check the second statement. It says that minus a to a f inverse x dx is always 0 for all a belongs to real number. Okay. Now we got the expression of f inverse x like this. So f inverse x is x plus x to the power 2n plus 1. Now as n belongs to natural number, so we can say that f inverse x is an odd function. That means from minus a to a, f inverse of x dx will be 0 for all a belongs to real number. So the second statement is also correct. Now let us check the third statement. From origin, two distinct tangents can be drawn to y equal to f inverse x. Okay. So the third statement we check, f inverse x is this. So let us draw a rough graph. This is the point 0, 0, and let us say this is the curve y equal to f inverse of x. Then let us assume a general point here on this curve. We assume a general point on this curve as t, t plus t to the power 2n plus 1. So we know that the slope of the tangent at any point of this curve is given by derivative of this function at t, t plus t to the power 2n plus 1. So this we can calculate easily. It will be 1 plus 2n plus 1 times t to the power 2n. And we will be able to verify whether the tangents can be drawn from the origin to this function or not if we equate this slope of this tangent to the slope of the line joining origin and this point. So we get t plus t to the power 2n plus 1 divided by t is equal to 1 plus 2n plus 1 times t to the power 2n. From here we get, as t is non-zero, so we can say that 1 plus t to the power 2n is 1 plus 2n plus 1 times t to the power 2n. So this will be cancelled and then we are left with 2n times t to the power 2n is 0. But we are given that n is a natural number, so n cannot be 0. That means t should be 0 to satisfy this equation. But t is non-zero. That means from here we say no solution for t. That means no tangents can be drawn from the origin to this curve y equal to f inverse x. So option C is clearly wrong. Now let us check option D. It says for n equal to 1. So we take the case n equal to 1. We got f inverse x as x plus x to the power 2n plus 1. So it will be x plus x cube. Now we are told that this value is equal to 18. What is this? Let us write this in this page. 2 to 10 f of x dx plus f of 2 to f of 10, f inverse of x dx is equal to 80. We have to check whether this is correct or not. Now, what is this? This is a standard formula that you should remember, that a to b integral fx dx plus f of a to f of b integral f inverse x dx is equal to b times f of b minus a times f of a. This you have to remember. But how can we derive it? We can derive it by putting f inverse x equal to some variable t in the second integral. Then you will get f of t equal to x, so you can differentiate and proceed. Now, how to solve this? This will be simply 10 times f of 10 minus 2 times f of 2. This value we have to calculate. Now, how to calculate f of 2 and f of 10? Basically, we found an expression for f inverse x, but fx is not known to us. Fx is more difficult to calculate. So how can we find these values? We have to simply use the concept of inverse function. So we know that f inverse of f of x is x, and so is f of f inverse of x. So we have to use this piece of information. So from here we can tell that f of f inverse x is equal to x. Now we have to find the value of f of 10. That means this f inverse x should be 10. Now for what value of x? F inverse x is 10. As f inverse x is known to us, we can say by putting the values of x one by one, we can say that x equal to 2 will give us f inverse x equal to 10. That means if we put x throughout this equation, we get f of 10 is equal to 2. Similarly, if we consider the other case, that f inverse x is equal to 2. So for what value of x, f inverse x is 2. F inverse x is 2 when x equal to 1. So this is true, implies f of 2 is equal to 1. So the value of f10 times 10 minus 2 into f2 comes out to be 20 minus 2, so 80. That means this statement is correct. So option D is also correct, which means that option A, B and D are the correct options for this question. I hope you understood this question.